Hello, uh, here is Emmanuel Markoulakis from the Hellenic Mediterranean University. I will present you today an interesting topic, theoretical quantum physics topic, which is related to the physical origin of the intrinsic one-loop anomalous magnetic moment of the electron. So we know the electron has an intrinsic magnetic moment, and because it's exactly intrinsic, it's actually unknown what is the actual mechanism of the generation of this anomalous magnetic moment, and it has the normal magnetic moment, which is defined by the Dirac G factor equal to, but you know the Fermilab experiments the last years has measured very accurately an additional perturbation factor of the anomalous magnetic moment, which is added to the normal magnetic moment of the intrinsic magnetic moment of the electron. And but there is no actually physical description explanation for where this anomalous magnetic moment component comes from. So the explanation, the conventional explanation, is that it is the interaction of the electron with a vacuum, with a quantum vacuum, which has all kinds of virtual particles, and this interaction creates this anomaly. So yeah, and this is called actually the dressed electron. So when the bare electron uh, interacts with its vacuum quantum vacuum environment, it creates the dressed electron, which includes the vacuum interactions, and these interactions are responsible, according to conventional quantum and electrodynamics theory, to for the anomalous dipole moment of the electron. But in my model and theory, the one loop, the first preparation term of the intrinsic magnetic moment, uh, and by extension the anomalous also a magnetic moment, is defined and controlled by the intrinsic mechanics of the electron. Because my electron is not a dimensionless point, my model is a finite geometric model of the electron, a field model, a wave model, a standing wave, a spherical model of the electron. So we have some kind of loops toy model created for the electron. And in my model, the reason is intrinsic for the one loop, the first order, the Schwinger term, the first order of the anomalous magnetic moment is for this is responsible actually 100% the geometry of the charge flux of the electron. So the electron is this is from there stems this anomalous behavior from the intrinsic geometry of the charge flux of the electron, according to my model and theory. Yes. So I will make a very short presentation now about this. I, I have a few slides to share with you, and yes, present now. I will present now. Give me a minute, please. Yes. So yes. So according, I have written a short paper uh, about this matter, and the reason, the real reason, as you will see now, for this anomalous behavior is exactly. But first let's make a bit more visible, larger the presentation here. I think yes. No, I think it's good. Yes, I think it's good. So that's true. I think this one is the best. Yes. So let's continue now. So here, to cut it short, and the short explanation is that the reason for the one loop anomalous magnetic moment is that the poloidal here radius, the poloidal periphery, is shorter than the equatorial. So this is the charge flux manifold and theory of the electron. It's a standing a soliton practically. It's a standing spherical wave made of electromagnetic flux. It's not much different from the field and the flux we see around and inside a permanent magnet or an electrical solar around and inside an electrical solenoid. So you have the flux around, and then you have a center of straight a flux tube, which is going like similar to inside a magnet or inside an electrical solenoid. And my theory predicts a model that this radius here, the poloidal radius, which connects the north pole and south pole of the electron, the north and south pole magnetic poles of the electron. So the electron is also called a quantum magnet, and this is the magnetic vector here, the magnetic moment, yes, south to north. And so it has the charge flux is it's a spheroid, a Hahn-Torr spheroid specifically. That's the mathematical description, and the flux is going inside and flowing outside from north to south and inside the manifold from south to north. So this is the flux tube, and my model predicts the exact reason for the anomalous magnetic moment is because there is an inhomogeneity in the fact that the poloidal radius here from center to the north pole is shorter than the equatorial radius from the center to the equator of the charge flux manifold. And that creates the anomalous magnetic moment. So it's in the anomalous magnetic moment of the electron is 100% intrinsically always the one loop, the first perturbation term, the Schrödinger term, is because this inhomogeneity in the geometry of the charge flux. Yeah, so we can see the periphery here, the perimeter, whatever you call it. So perimeter, we call it perimeter if it's a circle, but if it's a sphere, it's a periphery. So the periphery of the sphere, the poloidal going around the south and north poles, is shorter than the periphery going around the equator. That's the reason. And how much shorter, if you want to quantify it, my theory predicts that this anomalous, the anomalous here segment of curvature that is missing along the magnetic moment axis and along the poloidal radius, compared to the radius here at the equator, this curvature, this radius, the segment of the radius segment that is missing, this anomalous radius which is missing, is equal to the non-classical radius of the electron, which is, it's a known value, it's a constant, and it's about 2.82 femtometers. So femtometer is, 1 femtometer is minus 15 power of 10 meters. So it's a very short, and you can now see here why this is, because my model predicts that in the north and south pole there are two apertures, two vortex apertures of energy, which create a dip here. So if you symptotically here tangential follow the curve, yes, and you reach here above the poles, then you will create here a hasp because the vortex going inside, a dip, and this missing radius is equal to the anomalous here radius, this segment here, which my theory now defines and actually calculates that is equal to the classical radius of the electron. So the classical radius of the electron in my model is also here. The radius of this here. Imagine it like this is a horn tube, a flux tube. It's imagine like a straw, and it has a cylinder, a tube, and has an empty space inside. So there's actually here a radius involved, and this radius, my model calculates, is equal to the classical radius, which is actually the missing curvature. It's directly involved with the calculation of the missing curvature of the electromagnetosphere of the electron charge. Yes. So now let's quantify and calculate all this. So we have here the anomalous magnetic moment. This is the Schwinger term, which is G minus 2, the G factor. But the G factor, not the Dirac G factor equal with 2. It's the one loop G factor, which is slightly a bit larger than 2. It's actually, if I remember correctly, it's 2.0023 and some more digits. And this was actually it's a dimensionless value, and this was very with 2.5.2 sigma precision measured last year from the Fermi lab. It's you cannot. It's also referred as the most precise measured value, physical value in physics, in the order of 11, 12 decimal digits. And this now, Schwinger calculates this, the famous Schwinger term, which Schwinger put actually on his grave plate when he died. It's equal to the fine structure constant divided by 2 pi. And this again a dimensionless number. Of course, the fine structure constant alpha, don't confuse it with the anomalous magnetic moment. This is the fine structure constant, which is one of the most important constants in nature and physics, and it's approximately 1/137, and it's very tightly related with this charge flux geometry, intrinsic charge flux geometry. My model predicts for the electron. So yes, and so here is more analytically depicted my model. So my model predicts for the fine structure constant now that this is the ratio. Actually, this is not new. This is also known in conventional physics in the literature. But my model ties this up with a specific geometry, the specific charge flux geometry, because this is the classical radius of the electron. This is the reduced Compton wavelength, or else a Compton radius. It's this lambda, Greek lambda with dashed with a dash above. Don't be confused with the Compton radius, which is just with Greek L, this L letter without the dash, which is a different number. But this, of course, it stems out from the Compton radius. The Compton wavelength is related with the Compton radius, which is this lambda dashed here. So my model predicts that here the equator is the radius here at the equator is the Compton radius, or else the reduced Compton wavelength, which is this L dashed, and which is 3.86 power of minus 30 meters. This is known value in physics. And the thickness, the radius here of the tube, here inside the center, is the classical radius of the electron, which is 2.82 femtometers. Yes, and this is actually here where the mass of the electron, the center of the mass of the electron, is concentrated in this region here of the horn tube. This is called a horn spheroid, and this is the horn tube, which is actually a flux. Everything is here is flux, electromagnetic flux, and this is a flux tube. So yes, and this now the ratio of the radius here here at the center of this flux tube over the radius at the equator. This actually defines the fine structure constant value of 1 over 137. So it's actually the radius here, the radius of the flux tube here, which is the magnetic moment of the electron. This flux tube, this straight line consists actually the magnetic moment vector of the electron. This radius compared over the total values here at the equator defines the fine structure constant. This is a novel here equation, and which my theory predicts. So now going now back to the anomalous magnetic moment of the electron, we have the Schwinger equation. We have the equation here, which is the fine structure constant, which is the classical radius divided by the Compton radius, or else called reduced Compton wavelength. And the Compton radius is actually the Compton wavelength divided by 2 pi. So it's a radius. So if this is a radius and you have a 2 pi here in the denominator, this immediately geometrically equalizes the Compton wavelength with a periphery or a perimeter of a circle. So in my model, yes, my model, the Compton radius is this radius here, but multiplied by 2 pi, this radius makes up the periphery of this charged flux manifold here at the equator, the perimeter, the periphery, which is actually the Compton now wavelength. So the Compton wavelength here, which is about 2.42 picometers, it's minus 12 power of 10 picometers. The Compton wavelength is actually, in my model, the perimeter at the equator, the periphery of the equator, which is 2 pi, the classical radius. Yes. So the Compton wave, the classical radius is the Compton wavelength divided by 2 pi, or if you want the other way around, the periphery, the Compton wavelength is the Compton radius multiplied by 2 pi. Yes, that's very important. That's a very important detail we have to follow. So now combining all these equations, we get an alternative equation for the anomalous magnetic moment. The difference now here is that in the Schwinger term, you have a purely only dimensionless values. Fine structure constant is dimensionless, and but here we have tied the anomalous magnetic moment of the electron with actually length values. So this here is a length in meters, and this here also the Compton wavelength is also a length. So we have now derived that the anomalous magnetic moment is the classical radius of the electron over the Compton wavelength. Yes, not the Compton radius, the Compton wavelength. So it's telling us here geometrically now, because we have tied it also now to a geometry of the charge flux, all these parameters. What is the anomalous magnetic moment now physically saying geometrically is that this is somehow connected with a missing part of the periphery here of the curvature. So you have the charged flux sphere here of the electron, and the anomalous magnetic moment is a fraction of the equatorial periphery, which is missing. That is the physical meaning of this equation here. So how we can interpret this now? Simply, as I said before, it actually represents the missing component of the curvature here of the poloidal here periphery. So the periphery here at the poles is shorter by a segment compared to the periphery at the equator. And what is this segment? What is this curvature missing? What is this length? The length, which is missing, is equal to the classical radius of the electron. So the curvature which is missing is here, the segment, is 2.82 femtometers shorter than the curvature, the periphery here at the equator. The poloidal periphery around the north-south is about 2.8 to 2 femtometers shorter than in radius than the periphery here at the equator. Yes, the polluter is shorter than the equatorial periphery, which is the reason for the anomalous magnetic moment. We'll explain later that this is in radius, but in the curvature is something different. The curvature is something, it has to do with an arc, yes? So the calculation for the curvature, the basic curvature is different, as we will see later on. So yes, so now, yeah, this is the values here. I will link to the description of the video the actual paper, the preprint, so you can read it. This actually explains here all the values. This is the anomalous, the one loop anomalous magnetic moment of the electron. It's a terminology. This is the fine structure constant. This is the Compton wavelength, which is about 2.42 picometers, and it's equivalent in my theory to the equatorial periphery of the charge flux spheroid manifold of the electron. This is the lambda dash is the reduced Compton wavelength, which is actually this value here, the Compton wavelength divided by 2 pi. And it's also called Compton radius, and it's non-value. And code data gives this value to about 3.886 power of minus 13 meters. So it's about 38.6 picometers. And this is the G factor, the one loop G factor, which is a bit larger than 2. It's 2.00323. But the pure theoretical value, the direct value, is actually G equal with 2. Okay, this is the classical radius of the electron, Re. It's 2.82 femtometers. And yes, that's the anomalous missing polluter radius, which is equal to the classical radius, the missing polluter radius. Missing for what? Missing for making the sphere a perfect sphere, because a perfect sphere is always 2 pi r, either in the polluter direction or in the equatorial direction. It must be always 2 pi r. But this is not a perfect now sphere. The charge flux manifold of the electron is not a perfect sphere. It's actually a spheroid. And what a kind of spheroid? It's a it's a horn torus spheroid. If you search in Google the term horn torus spheroid, then yes, you will see you will land to Wolfram alpha, and here the horn torus. That's the name. It's actually an existing geometry, which you can see and read more about it in Wolfram alpha. Essentially, it's a torus, but with a very short inner space. So there's a donut, but the donut has a very short, very thin hole at the center. That's the horn torus. Yes. And if you think about it, it's not much different from the field you find in an electrical solenoid. So you have this inside the solenoid, you have straight flux going in, and outside you have the other flux which is going in the periphery around. And the same also holds for a permanent magnet. Yes, the flux inside the bulk of the material of the magnet is straight, but outside it curves and encompasses the whole area around the permanent magnet. So it's, the flux of the charge flux of the electron is nothing different actually, but only it has now a spinning motion, a physical motion. My model predicts. So it's a semi-classical model. And no, it doesn't. The tangential speed here in my model does not exceed the speed of light. So you will find my model linked in the description, the references of my model and all the relative papers. Okay, the model is called a half spin charge flux model, fiber model for the electron. That's the name of the paper, which describes the basic theory behind the model, this model. Yes. So this was the geometric analysis, but it was dimensionless. But let's now actually calculate the real in ampere meters squared units, the real anomalous magnetic moment contribution, and see if the theory, my model also predicts the same. So if you go to using conventional now theory, the Dirac electron, which has a G factor of integer 2, no decimal points, has an magnet, not now anomalous, but the normal magnetic dipole moment of the electron is equal with one Bohr magneton. So the Bohr magneton here has a value of 9.27 minus 25 over 10 ampere meter square units. So this magnetic moment units, so in SI units, and that's the classical, the electron without the anomalous magnetic moment has one Bohr magneton and magnetic moment. Yes, and perturbational theory says that this is a constant, but there's another constant, and this anomalous magnetic moment, which is added to this value here. Yes, to the normal magnetic moment. And this makes the total magnetic moment of the electron, which is also measured in big labs like Fermi labs and so on. So, but in order now to calculate this component, the component which is added of the anomalous magnetic moment, we have simply to multiply this ratio found before, the Schwinger term. So the Schwinger term is this here. Yes, this is the Schwinger term. Okay, this is my definition, but it's actually the same with this here. This is the Schwinger term. So using the fine structure constant over 2 pi, which this calculates always the first perturbation term, the one loop calculation of the anomalous magnetic moment and also magnetic moment of the electron. So if you multiply this dimensionless number with a normal magnetic moment of the electron, which is one Bohr magneton, this will give us the contribution of the anomalous magnetic moment, which we see here is calculated to 1.077 minus 26 over 10 ampere meter squared. So it's a very small fraction here. Yes, about 100 times smaller than the normal magnetic intrinsic magnetic moment of the electron. Yes. So, but there's another equation I have developed and I have derived, which says that the Bohr magneton, which is the normal magnetic moment of the electron, is equal to this here constant equation. It has no free parameters. It can use only with these values. You don't have the right to change anything here. So this calculates the normal magnetic moment of the electron, which is one Bohr magneton, and it is the charge of the electron multiplied by the speed of light in the vacuum, the reduced Compton wavelength or else Compton radius, divided by the Dirac G factor, the Dirac value, which is exactly 2 without any decimal component. And this gives the same exact here previous calculated value for the Bohr magneton, for the normal magnetic moment of the electron, which is 9.27. So it's the same value calculated here using a different equation, the Schwinger term, which is fine structure constant divided by 2. Yes. And so yes. So now if we however now use effectively to calculate what is the anomalous magnetic moment of the electron, we have now to put here the direct factor is the same, but we use now a different radius, which is this missing curvature. So if you put now this missing curvature here, the missing curvature here in this instead of the Compton radius, you have because now we have effectively this to calculate this contribution. So then this results to using the previous calculated predicted classical radius of the electron, using this quantity here as the periphery, this missing curvature, the periphery of the missing curvature. So you do a different a new cycle now, which is having the periphery of this cycle. This the sphere, it's now a perfect sphere. Is actually the periphery is equal to this quantity here, to the classical radius. And then when you calculate now this missing curvature new radius, you find that has a classical, it has, sorry, yes, it has a missing a missing radius now of 0.448 femtometers. So we use now this missing curvature, which is equal from the from the poles of the or flat charge flux manifold of the electron. We use this missing curvature because that's what is our theory says here. Our prediction says here, as you can see, that the anomalous magnetic moment is actually a quantity, a length which is missing from the periphery. And from where is this missing? This curvature is missing, this curvature segment. It's missing from the poloidal periphery, and it's equal, this arc, this small segment is equal to the classical radius of the electron. So we use now this classical here radius to calculate a new periphery. Equal, this radius here is actually now equated to the periphery of the missing curvature of this draws a circle actually, with it has periphery this here value, this classical radius, and then we calculate for this classical periphery, for this classical radius periphery, we calculate the missing radius this time, and the missing radius is 0.448 femtometers. This is the one loop calculation of the anomalous magnetic moment. This is anomalous radius calculation, the one loop of calculation for the anomalous missing curvature, which is translated now to radius. So the missing curvature, again, because it's this point is a bit not very difficult to understand. The missing curvature is RE, okay? The missing curvature is RE, but it's not in the model. It's not a radius. This is a missing segment actually. That's what our theory here predicts and calculates. This is a segment. It's a missing curvature. So you create another circle using this missing curvature, this circle, and then you calculate the radius which corresponds to this missing curvature. And the corresponding now radius we have calculated here. You can read that analytically in my paper. I will link inside the description. The missing now radius, which represents the missing curvature, is 0.448 femtometers. And when you now put this value here, this radius in the equation, so instead of the classical now of the Compton radius, in order to calculate the anomalous magnetic moment, you put now here the one loop calculation radius, this radius here. Yes, you put this one here instead of the Compton radius. You put the one loop anomalous radius, the missing radius, and then you will find the exact values we have actually calculated conventionally using the conventional Schwinger term definition of the anomalous magnetic moment. Using now this alternative method, the geometric method, we find the exact same number 1.077 minus 26 over 10 ampere times meter squares, which is the exact same value we found conventionally here in equation 6, where we used the definition of here we use the definition of the anomalous magnetic dimensionless value, which is the Schwinger term, is this term here, the Schwinger term. So first we calculate conventional the anomalous magnetic moment in SI units, which is using the Schwinger term, and we found yes, we found here the contribution of the anomalous magnetic moment, and then you see here, and then we did an alternative calculation using now my equation, this geometric equation, equivalent equation for the calculating the magnetic moment, and we calculate the same again quantity using now this here equation, which is using this missing curvature radius, the one loop missing anomalous radius. So this is actually the result found in equation 10 is an exact match with the previously found in equation 6 using conventional theory. So please notice also that our quantitative analysis using the normal known and measured Dirac constant value G equals with 2 and not Dirac value G is with 1. Why I say that? Because most of these semi-classical models hit the same wall. So the wall is that they only compute if they use a G factor with a classical G factor of 1. But we have measured in the lab that the G factor is the quantum G factor is not actually it's not 1, it's 2. But my theory uses the correct measured known value of the G factor, the Dirac G factor, which is 2 and not 1. That's my point, just to make this clear, that it may be a semi-classical analysis, but it actually complies and aligns with the quantum findings of quantum mechanics and experiments. So yes, these are the two papers. The equation, the citation 2 is the base model description. Yes, it's the most fundamental description. And this is a subsequent publication which talks about this anomalous magnetic moment and some other subjects. So yes, so yes, yes. So this was the demonstration. Thank you very much for your time. I believe you might find this uh, interesting. Yes, and this is Dr. Emmanuel Markoulakis from the Hellenic Mediterranean University. Thank you very much.